Myself, Dr. Sanjay Mathur, working as Assistant Director at Government Ramchandra Khaitan Polytechnic College, Jaipur. I am having 29 years of experience in technical education department at different positions. I have a background of structural engineering. Under the area in mechanics, I'll be focusing on the subject applied mechanics. It deals with the application of forces applied to the stationary and dynamic bodies. For knowing the stability of structure, the forces applied at different points and their study of input is very important. The stability or equilibrium of any structure that needs to be known, the centroid of the body. Centroid is a point which is geometrical center of plane area for two-dimensional figure like rectangle, square, triangle, semicircles, trapezium, etc. It requires only area but not volume, whereas volumetric bodies are three-dimensional bodies with a shape of cuboid, cube, prism, cylinder, sphere, cones, etc. Centroid coincides with the center of mass or center of gravity. It is same only if the material comprising the body is uniform or homogeneous. Center of gravity is the point where the total weight of the body acts, while centroid is the geometric center of the object. An object of any shape will be balanced perfectly on its centroid. When doing construction, one needs to make sure that it is being balanced with minimum stress. We have some standard shapes like rectangles, squares, triangles, circles, semicircles, quarter circles, trapeziums, etc. For those shapes, we know the areas and center of centroid of those figures. So, but in real life, we have composite figures which are made by minimum of two figures or more. So, finding centroid means finding coordinates with respect to axis like Cartesian system. So, we have the figure first rectangle. It's a dimension B and D. The area will be B into D and x bar will be B by 2 and D by 2. The centroid will lie on the intersection point of the diagonals. Similarly, square ring side A area will be A square, and the centroid will lie on the intersection of the diagonals, that is A by 2 and y in the y dimension A by 2. And if the tilted square is there and diagonal be known, then area will be diagonal square by 2 and the centroid coordinates will be A by root 2 and A by root 2. Similarly, for the triangles, we have right angle triangle. The area will be half into base into height, and the centroid from the x point of view, it will be b by 3 from the 90-degree angle and h by 3 in reference to the y-axis, y bar. That will be the intersection point of the medians. Similarly, for the isosceles triangle with the base width and height h, the area will be half into base into height, and the then x bar will be b by 2 and y bar will be again h by 3. And another triangle like oblique triangle where the base is of length AL comprising with A and B. That means A plus B is equal to L divided from the vertex point of view. The area will be half into L into H and the centroid x bar will be A plus L by 3 from the A side. And if you want to measure from B side, that will be B plus L by 3. And in the y-axis reference, y bar will be h by 3. That will be again the intersection point of the medians. Come to the next figure, that is trapezium having two parallel sides A and B. The area will be half into sum of parallel sides into height, and the centroid will lie at y bar That will be a plus 2b into h upon a plus b into 3 if we measure it from the a side. If you want to measure from the b side, that will be b plus 2a into h upon a plus b into 3. Similarly, other figures, curved figures like circle, semicircle, quarter circle. For the semicircle, we have area of pi r square by 2 if the radius of the circle is r, and y bar will be 4r by 3 pi from the base. That will lie on the line of symmetry. And again, for the quarter circle, the area will be quarter of the area of circle. That will be pi r square by 4. And in the x term and y term, that will be again 4r by 3 pi. So these are the curved segmental circle. Now, for getting the centroid, means we have to find out the coordinates with respect to any axis according to the Cartesian system. So for the figure, we wanted to know the centroid, we have to divide the figure among some standard shapes like in triangle, rectangles, square, semicircle, or whatever areas we already know, and CG of those figures we already know. The formula will be x bar will be a1 x1 plus a2 x2 plus a3 x3 plus a4 x4 and so on, divided by a1 plus a2 plus a3 plus a4. And similarly for y, again it is a1 y1 plus a2 y2 plus a3 y3 plus a4 y4 upon a1 plus a2 plus a3 plus a4, like sigma ax upon sigma I and sigma ay upon sigma I. So by this formula we can calculate. Let us take an example of channel section. Channel sections are used in steel structures construction, railway stations or industrial sheds, where this channel section are being used as a beam section or as a column section or as a strut section. So this is the cross-sectional area of a channel section. So this is a C-type shape of alphabet C. It is size 20 from the base, and the depth of the section is 40 mm and width of the section is 10 mm. Now we have to find the centroid of this channel section, which is a two-dimensional plane lamina. We want to know the centroid of that complete section. So first we will divide the figure into number of standard shapes. So here the standard shape looks like rectangles. Rectangles, we already know the areas in centroid. Now we have to check the symmetry of the figure by cutting the figure into two geometrically equal parts. If the figure is symmetrical about any axis, the centroid will lie on that axis. That is called line of symmetry. So by cutting it through x-axis, we see that the figure is completely divided exactly into two geometrically equal parts. It means the figure is symmetric about x-axis. But if we cut by y-axis, it will not divide exactly among two geometrically equal parts. That means we know the y bar. Y bar will be the total height of the figure divided by 2. Total height of the figure is given 40 mm, so 40 divided by 2, that will be the y bar. So y bar will be 20 mm. Now we have to calculate x bar. So we have to divide the complete figure among the known shapes. Here the known shapes are rectangles. So we are dividing the rectangle among three number. One rectangle is A, B, C, D dash. Second one is D dash, D, E, E dash. And third one is E dash, F, G, H. So first rectangle A, B, C, D dash, that dimension are 20 by 10. The area will be 20 into 10, 200 mm square, and x1 will be 20 by 2. We are measuring from the y-axis. So that will be 20 by 2, 10 mm. Now taking second rectangle, area will be again 20 by 10. Now x2 will be 10 by 2, measuring from the y-axis. That will be 5 mm. Again taking area of third rectangle, that is 20 by 10 side. Area will be 200 mm square, and x3 will be again measuring from y-axis, that is 10 mm, 20 by 2. Now putting all the values of A1 x1, A2 x2, and A3 x3 in the formula, we find out the value of x bar, that will 8.33 mm. So the centroid coordinates are 8.33 mm x and y bar is 20 mm. So we can see that with reference to our 0, point, this putting the channel section in the first quadrant, we are measuring all the distances in x dimension and y dimension in the positive. So this way we can find out the centroid of a symmetrical section in one dimension. Now come to the second figure, that is the F-type shape. This is unsymmetrical section. As we divide the complete figure among two parts by cutting it centrally along with two axes, one with x-axis and other one with y-axis, we see that if we cut the two-dimensional figure f by x-axis from centrally, it will not cut the figure exactly into two geometrically equal parts. And exactly happens same if we do with the y-axis. It will not divide exactly into two geometrically equal parts. So it means it is not symmetric about x-axis and not symmetric about y-axis. So we have to find out the centroid coordinates in terms of x bar and y bar. Now let us divide this F section into four rectangles. First one is ABC C dash. Second rectangle is C dash D E F dash. And third is F dash F G G dash. And fourth is G dash H I J. So these four rectangles area we already know, and we know the centroid of all the rectangles. So let us take first rectangle. First rectangle dimension are 90 by 30. So area will be 2700 centimeter square. X1 will be measured from this y-axis, that will be 30 by 2, and y1 will be measured from x-axis, that will be 90 by 2, 45 centimeter. Come to the second rectangle. Again the area is 90 by 30. 2700 centimeter square. We are measuring x2, that is 90 by 2, and y2 will be, because measuring from the x-axis, it will be 90 plus the 30 by 2, that will be 105 centimeter. Now come to the third rectangle, that is again 60 by 30. The area we can multiply it 1800 centimeter square, and x3 will be 30 by 2, and y3 again we are measuring from the x-axis, that is 120 plus 60 by 2, comes out 150 centimeter. And come to the last rectangle, fourth, A4 will be 120 into 30, that will be 3600 centimeter square. X4 will be 120 by 2, and Y4 again measuring from the x-axis, that will be 180 plus 30 by 2, that comes out to be 195. Now putting all the values of A1 x1 A2 x2 A3 x3 and A4 x4 in the formula, divided by A1 plus A2 plus A3 A4, we find out that 35.25 centimeters is x bar, and similarly y bar is coming out to be 127.50. So we see that this coordinates of the centroid doesn't lie in the boundaries of the figure. So sometimes the centroid may exist outside the boundaries of the figure. In this case, we are seeing. Now we move to the another section. That is, we have this is the given of a shaded part. Uh, it is a red color shaded lines are there. That complete shaded area, for that area we have to find out the centroid. So in a composite body or composite figure, it has a hole. Here we are seeing that there is a hole or geometric region having no material or area. Then consider the body without the hole and consider the hole as an additional composite part having negative weight or size. So to solve this problem, we completely divide the figure among two parts, cutting it centrally along with two axes, x and y axis. We see that along the y axis, it is symmetric. It divides among two parts if we cut it centrally from the y axis. But if we do for the x with the x axis, it will not divide the figure into two parts. So x bar will be total width of the figure divided by 2. That is 15 plus 20 plus 15. That is the total width of the figure divided by 2. Putting the figure in the first quadrant of the Cartesian system, x will be taken positive and y will be taken positive. So we are taking this as x is most bottommost side of the figure and y as extreme left side of the figure. So putting the section in the first quadrant, uh, we divide the figure among two parts. First one is top portion is looking like trapezium of top width 40 centimeter and bottom width is 50 centimeter. Parallel sides and 25 centimeter distance among the parallel sides. And second one is the rectangular part, bottommost portion. And this third and fourth portion is the inner whole part that we have to deduct, which we are calculating in this second area. So let us take the area and coordinates of the first trapezium. First trapezium, the area will be half into sum of parallel sides into height. So that is coming out 562.50. Now we have to measure the distances from the x-axis. So 25 plus we are measuring from 50 centimeter side. So that will be a plus 2b into h divided by 3 divided into a plus b. So it is coming out 12.03 centimeter. Now look the second figure, that is a rectangular figure having dimension of 50 by 25. The area will be 1250 centimeter square and y2 will be 25 by 2 because measuring from the x-axis. So these two areas we know. Now this is the deduction part. A3 is the rectangular part 15 by 20 centimeter. Area we can calculate 300 centimeter square and y3 is 15 by 2 and x3 will be because measuring from the y-axis it will be 15 plus 20 by 2, so that is coming out to be 25 centimeter. Now last figure is fourth, which we have to deduct, that is semicircular. The area will be pi r square by radius is 10 centimeter, so area is coming out 157.14 centimeter square. Now y bar will be 15 plus 4r by 3 pi. So it is coming 19.24 centimeters. So that area we have to deduct. The formula will become a1y1 plus a2y2 minus a3y3 minus a4y4 divided by a1 plus a2 minus a3 minus a4. So the y bar is coming 12.63. The centroid will again lie in that whole portion, that is from the extreme left side and bottommost side. It is 25 centimeter extra in the x term, and in the y term it will be 12.63 centimeter. Coming to the another section, that is the look like a dam section of a plane lamina. We have to find the center of the dam section, but all the time in previous figures we had choose the reference axis with our own choice. This time we don't have our choice to choose the axis. The axis has already been given in the figure. These red color lines x and y, they are given. We have to find the centroid with respect to these reference lines, these reference axes. So to solve this problem, we are putting these reference axes. The 0, 0 origin is given. We see that half of the figure lies in the first quadrant and some part of the figure lies in the second quadrant. In the first quadrant, we know x is positive and y is positive, but in the second quadrant of Cartesian system, we know x is negative and y is positive. So for solving this problem, we have to take consideration of the signs of x and y with reference to these x's. So we divide the complete figure among two parts with reference to x-axis and y-axis. We find that this is not symmetric about any axis. We have to find out the x bar and y bar for this dam section. So first we take the first part, that is triangular portion. Second one, we take the complete rectangle. This third part we are covering among inside the second rectangle. The first rectangle uh, area is half into 3 into height. Base is 3 and height is 3. So that will be 4.5 meters square. X1 will be in the right angle triangle, it will be b by 3, and in terms of height, it will be h by 3. So 3 by 3 and 3 by 3, 1 meter, the centroid. Both will be positive because they lie in the first quadrant. The second rectangle, we had covered third rectangle also. This is behind this rectangle. The area will be length into breadth 3 into 3, and x2 will be in negative direction. It lies in the second quadrant. That will be minus 3 by 2 minus 1.5, and y will be positive. That will be 3 by 2 plus 1.5. And this is the rectangle third, which we have to deduct, which we have covered in second rectangular portion. So the area is 2 into 1, and x3 will be again negative. That will be measured from the y-axis. That will be 2 plus 1 by 2, and in the negative side, so that will be minus 2.50 meters. And y3 will be again measured from the x-axis, that is 1 plus 2 by 2. So putting all the values in the formula a1x1 plus a2x2 and deduct that portion which we had covered, that is minus a3x3 divided by a1 plus a2 minus a3, and it is coming out minus 0.347. It means it lies in the second quadrant. It is behind the y-axis from 0.0347 meters. So come to the y bar. Again, putting all those values, we are getting 1.217. It means the centroid will lie in the second quadrant, and the coordinates will be with reference to given axis, red colored axis, it will be behind that, and 0.347 minus and 1.217 meter plus. This will be the coordinates. So this is the example where we have already given the reference axis. According to them, we have to find out the centroid of the given section. This is another problem of shaded area. The shaded area, this red color parallel lines, it's again part of the segmental circle. Uh, Such kind of problem, we can do one thing. This is the bottommost portion is 5 centimeter. On the left hand side, if we could extend the vertex of the figure to the vertically downwards, and similarly we extend the given horizontal dimension 5 cm on the left side, where they will meet, we assume the origin 0, 0. Now the problem looks like a quarter circle problem. So it is quarter circle and triangle. If we take as a complete quarter circle and deduct that triangular portion, we will get our shaded portion. So let us divide into two parts. One is quarter circle. First figure will be the area will be pi r square by 4. It is 157.14, and y1 will be 4r by 3 pi. So we can find out both the values. 4.24 centimeters are coming, and coming to the second figure, that is triangular. The area will be half into base into height. We will have 25 centimeters square, and again this is x2 is 5 by 3, right angle triangle, and again it is 10 by 3, b by 3 and h by 3, 3.33. And putting the value in formula a1 x1 minus a2 x2 upon a1 minus a2, we are getting 4.72 centimeters, and this is 4.41 centimeter. So this centroid will lie at, from the reference 0, 0, which we had assumed, it will be there. So this is another problem. So centroid is an important parameter of engineering problem. It also always helps to find the stability of any structure. Suppose a carpenter has to make a wooden table of top triangular shape. So the one leg support we have to give, that will be the best position where it will be stable. That will be the centroid of the table. And in construction also, for properly balance the structure with minimum misses, we need to calculate it. This is the Burj Khalifa, which is 2,770 feet high. This is the tallest building of the world with more than 160 stories. It resists the forces of nature such as wind, seismic, and gravity. We can see the gravity load flow line. It's a stable structure and miracle for the building site. The Burj Khalifa still for confusing the wind. The chief structural engineer Bill Baker calls it just one of the methods used to help super talls resist wind stresses. Another example of Leaning Tower of Pisa, situated in Italy, it is 14,500 metric tons. Its geometry thin at the top and thick at the bottom. Its center of mass exists somewhere lower than the top of its fourth floor. In the year 1990, the tower reached to the inclination of 5 degrees. Engineers that its center of gravity was coming dangerous. Engineers warned close to the outer edge of the base means the tower was coming close to the fail. In the end of the leaning tower of Pisa does not fall because its center of gravity has been carefully kept within its base. Any object stands until line draws from its center of gravity to ground falls within its base. In the figure we see that base first figure stands stable, second figure again stands stable, third figure again stands stable, but in the fourth figure this center of gravity is outside the base. So that means this is the failure sign. So this leaning tower of Pisa is still standing just because of the center of gravity lies still in the bottoms. It is not going outside the bottommost line of the base. So this another example of bus. The center of gravity of bus is close to the lower side of the complete body. If it rises to the higher side, the bus will flip at the turns. It should be designed such that the center of gravity should be kept at lower side of the bus. By this way, we can conclude the gravitational forces of the elementary parts of body is composed can be replaced with the action of resultant force with intensity as large as the weight of the body directed at the center of gravity of the body. And center of gravity is located at the intersection of gravitational lines and in the correct geometrical bodies is determined geometrically. This is true if the density of the substance throughout the body is same, that the body is homogeneous. In that case, the center of gravity is equivalent with the centroid of the body. The centroid means it is the average position of all points of an object. It is a point at which is a cutout of the shape could be perfectly balanced. So centroid and center of gravity and center of mass is very important for stability of any structure. By this way, I conclude this topic and hope must like. Thank you.